Welcome to this session on signals and systems. So this is the first unit in signals and systems. This unit I will be covering in two parts, that is part A and part B. In part A, we will be discussing the signal analysis, and in part B, we will be discussing signal analysis in the vector domain. So let us get started. First, we will be discussing classification of a signal, and we will be discussing the classification of the systems. And we will also be discussing the elementary signals in this video session. So before we go ahead, let us define what is a signal and what is a system. So basically, a signal conveys information and it is a function of one or more independent variable. So a signal should be characterized by these two quantities. That is, it has to contain an information and it should be a function of one or more independent variable. So if the function is dependent upon one variable, we call it as a single dimensional signal. If it is depending upon two independent variables, then we call it as a two-dimensional signal, and so on. So that is about the signal. So it should have the information and it should be a function of one or more independent variable. Let us look at some of the examples of signals. Voice signal, video signal, signals that are on the telephone wires, ECG signal, EEG signal, etc. These are some of the examples of what a signal is. Now, the signals can be continuous in time or it can be discrete in time. So why we have to make this distinction? The discrete time signals, we can use it to process it on the computer. All signals, they exist in the form of a continuous time signal, like for example voice signal, whatever we talk, or the ECG signal, they all exist in continuous time domain. So the continuous time signal has to be converted into a discrete time signal. So continuous time signal means it exists for all time values, and discrete time signals means they exist only for discrete or integer values of time. So we will see how we distinguish between them in the later discussions. Next, let us look into the system. A system is a device or it is a combination of devices which takes in the input and it performs some operation and produces some output. The output, we call it as a response. So the system is a device or a combination of devices that takes in the input signals and produces an output by performing some operation. So the input, we call it as the excitation, and the output, we call it as the response. Example is a simple communication system. It can be the AM radio or the FM radio. It is a simple communication system. So you can have many inputs to a system and it can have one or more outputs to the system. So the system can have multiple inputs or single input, or it can have single output or multiple outputs. So we have just defined formally what is a signal and what is a system. Now let us look into the representation of Discrete time signal. As I said, discrete time signal exists for discrete or integer values of time. So let us see how we can represent them. So we can represent the discrete time signal in four different forms. First is the graphical form, second is the functional form, third is the tabular form, and fourth is a sequence form. Whereas the continuous time signal you can represent using the graphical form or the function form. Now here shown is the graphical form of a discrete time signal. Now this is what I mean by saying discrete time signal. So here the x-axis I am calling it as n, and the y-axis I am calling it as x of n. Now let us look into each of this. So n takes on the values here as -2, -1, 0, +1, +2, and +3. So n does not take any fractional values. N takes only integer values. So it can be positive or negative. And so n is an independent variable here. So x of n is a function, and x is a dependent variable, and n is an independent variable. So x of n represents the amplitude at the value n. So here, if you see the first sample at n equals -2, the amplitude is -3. So that means at n equals -2, x of n takes the value -3. At n equals -1, x of n takes the value +2. At n equals 0, the amplitude or x of n value is 0. At n equals +1, the signal takes the amplitude +3. At n equals +2, the signal amplitude is +1. At n equals +3, the signal amplitude is +2. So this is what we call it as a graphical representation. So we understand how this signal is represented. Now let us look into the functional representation. Now this takes quite a lot of space to draw this signal. Now you see this is the functional representation of the signal, which takes just two lines to represent this. So here we see that x of n represents the amplitude, and n is a different values instance. So here the function says that x of n equals 2 power n for n equal to 0 or greater than 0, and the amplitude is 0 for n less than 0. That means the signal exists only for n greater than or equal to 0. So that means if n takes -1, -2, -3, etc. up to -infinity, the signal value will be 0. Now for n taking value 0, +1, +2, +3, etc. up to +infinity, x of n has a function value 2 power n. Now at different values of n, we can compute this signal. Now at n equals 0, we get x of 0 is equal to 2 power 0, which is equal to 1. So x of 0 will be equal to 1. But n equals 1, x of 1 equals 2 power 1. So 2 power 1 is 2. So x of 1 will be equals to 2. At n equals 3, x equals 2, x of 2 will be equals to 2 power 2, that is 4. At n equals 3, x of 3 will be equals to 2 power 3, that is 8, and so on. So this signal will continue as long as n is continuing. So here in this first graph, what we have shown here, we have shown it is a finite signal, whereas this, it can be an infinite depending on the value of n. So here we are saying that n is greater than or equal to 0. That means it can go on up to infinity. So therefore we can't draw a signal up to infinity. So therefore this represents a very concise form of representation. So I hope now you are able to appreciate the difference between these two representations. So if you want to represent the signal, which is a very long signal, we can't represent the graphical form. We can go for the function form. If it is a very small, very short duration signal, we can represent it in the graphical form, right? Now let us look into the tabular form of representation. Now this is the tabular form of representation for the same signal shown here in the graphical form. So n represents the first row and x of n, or the amplitude, represents the second row. So here n takes the one value -2, -1, 0, 1, 2 and 3, and x of n gives the amplitude at n equals -2, the amplitude is -3, at n equals -1, the amplitude is +2, and so on. So for this graphical representation, we have shown the tabular form. So either we can represent the discrete time signal in this graphical form or in the tabular form. So these two are the same signals, whereas the x of n, which is equal to 2 power n, it is a different signal. Now, if you want to represent in the sequence form, this is a lot more easier. So here the brackets shows the content of the signal. That means x of n is contained within this brackets. So here the arrow mark shows the where the 0 is. That means the n value 0, not the signal value. Where, see, as when you look at the graph, here there are two values. One is the n value and the other one is the x of n value. So we are talking of the n value 0. So that n value 0 is represented here with the arrow mark here. So which says the time instant 0. So this is another form. So this is called as a sequence form. So these are the different ways of representing a discrete time signal. If you are talking of the continuous time signal, we can represent it either in the form of a graph or in the form of a function. Okay, now let us look into the different elementary signals. The first signal is the unit step signal. So unit step signal is represented like this. So that means we are going to call that function as u of t. So it has a value of 1 for t greater than or equal to 0, and it is equal to 0 otherwise. So this is a graphical representation of the unit step signal or unit step function. So this is the signal. So for t, as long as t exists even, that means it can go up to infinity. So starting from 0 up to infinity, this signal will continue to have an amplitude of 1, a constant amplitude of 1. So in the function form, we can write this as u of t equals 1 for t greater than or equal to 0. It is equal to 0 for t less than 0. So this is the graphical form here, and this is the function form here. Now, this is a continuous time signal as it exists for all values of t starting from 0. That means if I say t is equal to 0.0001, that point comes after 0. So it exists. If I say 0.0009, so that point also comes after 0. If I say point or if I say 1.115, so that point comes after 0. So there that value also exists. So you can see that for all those values of t, the signal exists. So when then we say that the signal is continuous. So if we talk of the discrete time signal here, how we represent the same unit step function u of n. For a continuous time, we represent it as u of t. For a discrete, we represent as u of n, and n takes all integer values. So as I said, it can take value 0, +1, +2, +3, etc., or -1, -2, -3, etc. But it will not take the value of 0.001, 1.15, 1.013, and whatever number you say. It cannot take all those fractional values. It can take only integer values. So this is what we call it as a discrete time signal. So here we say this is the unit step function in the discrete form. So it starts at 0 and has a constant amplitude of 1 for different values of n, when n can take the value 0, 1, 2, 3, etc. So this can be written in the function form of u of n equals 1 for n greater than or equal to 0, and it is equal to 0 for n less than 0. So I hope you understood the difference between the continuous time signal and discrete time signal. Next, we will look into the ramp signal. So all these signals, whatever we are going to discuss, we will represent it both in the continuous time domain as well as the frequency, the discrete time domain. And then we will also represent in the graphical form and function form so that we can get used to it. Now, as I said, these are all signals which are existing till infinity. So we cannot, there is no point in writing the tabular form or in the sequence form, because we have to write values up to infinity, right? So we can restrict to the function form or the graphical form. The unit ramp function. So this unit ramp function is represented as r of t. It starts at t equals 0 and has a slope of 1 starting at 0 as t varies. So this is a graphical form, and we can represent in the function form of r of t is equal to t for t greater than or equal to 0, and it is equal to 0 for t less than 0. So that means, so at t equals 0, it is equal to 0. At t equals 1, the amplitude r of t is equal to 1. At t equals 2, r of t is equal to 2. At t equals 1.12, r of t is equal to 1.12. So this is the continuous time signal. So we are representing it as r of t. Now we can represent this unit ramp signal in terms of the unit step function as u of t into t, or t into u of t. So r of t is equal to t into u of t. So when we say u of t, it ensures that it starts at the value t, because t can exist for all minus values also. But to ensure that the signal starts at t equals 0, when we multiply with this signal u of t, so as we have previously defined, u of t starts at t equals 0 and continues for t greater than 0. So therefore, when we multiply this u of t with this t, we can be sure that the ramp signal starts exactly at the instant time t equals 0. Now let us look into the discrete form. We represent as r of n, and r of n equals n for n greater than or equal to 0, and it is equal to 0 for n less than 0. Again, we can represent it in terms of the unit step function as r of n is equal to n into u of n. Next, we look into the parabolic function. So in the function form, we represent this as p of t is equal to t square by 2 into u of t. So this is the parabolic function, p of t. In terms of the discrete signal, we represent as p of n, and we write it as p of n equals n square by 2 for n greater than or equal to 2. Again, we can represent it in terms of the unit step function also. Next signal that we are going to look at is the impulse function, unit impulse function. So unit impulse function is represented as delta of t. So it has an amplitude of 1 at time t equals 0, and it does not exist for any other time. It exists only at time t equals 0, and it has an amplitude of 1. So in the function form, we represented this as delta of t is equal to 1 for t equals 0, and it is equal to 0 for t not equal to 0. Now this unit impulse function has many properties. Let us look into the unit impulse time. This is we are looking at the continuous time because we are talking of t, delta of t. So it is an even function. That means delta of t is equal to delta of minus t. So we call this as a even function. And if you integrate minus infinity to plus infinity x of t delta of t, this integral will give you the value at t equals 0. So as we know, delta of t exists only at t equals 0. So even if you integrate the signal from minus infinity to plus infinity, you will get the value only at t equals 0. So therefore, when we multiply delta of t with x of t, which is some arbitrary signal or any signal, and when we multiply that and integrate it, we will get the signal value of x of t present at t equals 0. So we are going to get only one value at t equals 0. So this is what we call this property as shifting property. So we get only one. So if you are talking of some other time, not at t equals 0, but some other time called t naught, then we will get the function value of x, I mean the function value x of t at the value t naught or at the time instant t naught. So we get x of t naught. So integral minus infinity to plus infinity x of t delta of t minus t naught dt gives us x of t naught. So this we call it as a shifting property. So we pull out that value exact. So though x of t exists for different values, we multiply with delta of t and get just exactly one instant of time that we want, exactly at t equals 0 or at t equals t naught. Just at that time, what is the signal value? So this we can also tell as a sample. So that means x of t exists for different values of t. We want to sample at t equals 0 and get the signal value, or at t equals t naught we want to sample the signal x of t and get its amplitude. So this is what we call it as a shifting property of impulse function. Next is a scaling property. So delta of at, that means the time is scaled by an amount a, is equal to 1 by mod a into delta of t. So when you scale in time, it is equivalent to dividing the delta function by the scaling factor a. The next, even if we don't integrate, we know that when we multiply x of t with delta of t minus t naught, we get x of t naught. So that means the signal delta of t exists only at t equals 0. Okay, so at t equals t naught becomes 0. So delta of 0, so according to the definition, delta of 0 only is equal to 1, because we say that delta of t is equal to 1 at t equals 0, means that at 0, when t takes the value 0, at that instant only you get an amplitude of 1. So therefore del x of t into delta of t minus t naught gives us x of t naught. So by simply multiplying with the uh, delta of t minus t naught with x of t, we get x of t naught. So this t minus t naught, we call it as a time shift. We'll see this operation in the later topic, but just to understand here, we call this as a time shift. So instead of making this operation at t, we are pushing it to a some other time called t naught. So at instead of the uh, event occurring at t, we are calling it to occur at t equals t naught. So this is what we call the shifting operation. So if you don't shift, if you simply multiply with delta of t, so here we are showing it as x of t multiplied with delta of t is nothing but x of 0. Next, x of t can be obtained by integrating the function between the limit minus infinity plus infinity by with respect to the integral tau. So delta of t minus tau. So this, when we integrate with the time shifted impulses, we will get the entire signal x of t. So this is the reverse process. So here I said I get only one value of the, in the property number 2, I got one value of the signal x of t. Now if I add all those values, I can reconstruct the original signal x of t. So property number 2 and property number 5 are related. So in property number 2, I'm getting one value, and in property number 5, I'm putting all those multiple values and obtaining the original signal x of t. Next, we will look into the unit impulse function. So as I said, it is represented as delta, and since it is a discrete time signal, we will represent as n. So this is the function form and graphical form shown here. Let us look at the properties of the discrete time unit unit sample sequence. So delta of n equals u of n minus u of n minus 1. So if you take the signal u of n and subtract u of n minus 1. Now u of n starts at n equals 0 and u of n minus 1 starts at n equals 1. So when you subtract those two signals, you will simply get the signal delta of n. Delta of n minus k equals 1 at n equals k. So this is the time shifted sequence. So just like I have said in the continuous domain, you take the single value and add on all the single values, you will get the original signal. So that counterpart is property number 3. And this is the sampling part which we saw in property number 2 of continuous impulse function. Next elementary signal that we are going to look at is the sinusoidal signal, which we represent in the function form as x of t equals a into sine omega t plus phi, where a represents the amplitude, omega represents the angular frequency, and phi represents the phase. In terms of the discrete time signal, we represent it as x of n equals a into sine omega n plus phi. And the fundamental period of this signal is represented as capital T for the continuous time, which is given by 2 pi by omega, and omega is equal to 2 pi f, which will give T is equal to 1 by f. Similarly, for a discrete time signal, we call the fundamental period as capital N, and that we represent it as 2 pi by omega. And to make a distinction from the continuous time to discrete time, we add a parameter called m. Now why we add this parameter called m is that to make this fraction into a integer value. Suppose we divide 2 pi by omega, and omega is equal to, let us say, 3 pi. So if you add, or if you take the value omega is equal to 3 pi, then 2 pi by 3 pi, you get 2 by 3, and without m you get a value of n is equal to 2 by 3, which is a fraction. So n cannot take the fractional values. So we put this parameter m such that if m takes the value of 3, then capital N will get the value of 2, and 2 will be the fundamental period. So we add this m such that it converts this fraction into an integer. It can take, m can take any value depending upon the denominator here, so that the denominator is appropriately cancelled to make the capital N to be a whole number. So this is the discrete representation. Now let us look into the graphical form. So that is the phi represented here, which shows the phase angle. This is the discrete sequence. Next is the exponential signal. X of t is equal to a into e power alpha t, where a is the amplitude, and it can be represented in the discrete form as x of n equals a power n. So if alpha takes the value 0, then e power 0 is 1, so you will have a constant signal as shown here. If alpha is greater than 0, then you will get a signal which is a growing exponential. If alpha takes a value less than 0, that means it is taking negative values, -1, -2, or -0.1, 1.5, or it can take even a fractional values, because we are talking of a discrete, continuous time signal. So therefore, if alpha takes the negative values, we will get a decaying exponential. Next, if you want to represent in the discrete domain, then we call x of n equals a power n, and a is greater than 1, and this gives a growing exponential. And when a takes a value between 0 and 1, we get a negative, the decaying exponential. If a takes a value of -1, and -1 power n will take the different values, so for all odd and even values we will be getting, so you will be getting a signal like this. Here, when a is less than, in the previous here, when a is less than -1, we get the growing exponential with two polarities. That means we get positive values as well as negative values. Similarly, when a takes a value between -1 and 0, we get a decaying exponential with two different signs, that is positive and negative, alternating. Next, the complex exponential. So in the complex exponential, we are going to represent this as x of t is equal to a into e power st, where s is a complex variable. S is equal to sigma plus j omega. Okay, and e power j omega can be written as in the Euler form as cos and sine. So therefore, we are writing it as a into e power sigma t into cos omega t plus j sine omega t. So we can represent in the discrete time as x of n equals a power n e power j omega naught n plus phi. So omega naught is the fundamental frequency. In the previous case, here we have not shown the phase angle. Here we are showing with the phase angle. Now this is the complex signal by taking s equals 0, and when s is equal to minus sigma and s is equal to plus sigma. So when s is equal to minus sigma, we get a decaying exponential, and when s is plus sigma, we get a growing exponential. And if s is purely imaginary, we get the sinusoidal signal. If s is equal to sigma plus or minus j omega, then we get the decaying sinusoidal signal with when sigma is less than 0. When sigma is greater than 0, we get a growing exponential sinusoid. So for a discrete time signal, we have the growing exponential sinusoid and the decaying exponential sinusoid. The next signal is the rectangular pulse, which is represented as r of t or pi of t. So pi of t by tau is equal to 1. So it has an amplitude of 1 between the values minus tau by 2 to tau by 2. So this is the rectangular pulse signal. The next signal we're going to, I am not shown the rectangular pulse in the discrete domain. I've shown only in the continuous domain. It can exist even in the discrete domain. The next signal is a signum function, which looks like this. So it has a amplitude of -1 starting from -infinity up to 0, and at 0 it has a positive amplitude of 1 and it continues up to infinity. So this looks like two different uh, unit step signal. Of course, at 1 at t equals t greater than 0, and 1 the amplitude is negated for t less than 0. So in the function form, signum of t is equal to +1 for t greater than 0 and is equal to -1 for t less than 0. We can also represent the signum function in terms of the unit step function as -1 plus 2 into u of t. The other function is the sinc function. So this is how the sinc function will look like. It has a amplitude of 1 at t equals 0 and it dies down as t goes away from 0. So in the function form, we represent this as sinc t is equal to sine t by t for -infinity less than or equal to t less than plus infinity. So this is a sinc function. It comes in aid when we are talking of the uh, transforms. So these are the different elementary signals we have seen. So in this discussion, we have seen the classification of signals and classification of systems. We have seen some of the elementary signals both in the discrete time domain as well as the continuous time domain, and the representation of the signals we have seen. In the next section, we will talk about the basic operations that you can perform on the signals, and we will perform the classification of the systems, and we will also take up the part B in the upcoming sessions. Thank you.